Hello, everyone. Thank you for joining us for today's Deeper Talk seminar. My name is Jared Heiss, and I'm the Science Director at SURF. Before introducing our seminar speaker, a few housekeeping announcements. Today's event is online. Questions will be answered at the end of the presentation. Raise your hand in Zoom to ask a question live. You can also use the Q&A button at the bottom of the Zoom screen. This talk will be recorded and available to view on the website institute.surf/deeper-talks, as well as on our YouTube and Vimeo channels. If you wish to receive notification for upcoming monthly talks, go to the Connect link at the top of the Institute website. Now it's my privilege to introduce today's speaker. Dr. Joseph Formaggio is an experimental nuclear physicist at the Massachusetts Institute of Technology, where his work has focused on understanding the fundamental properties of neutrinos. His previous work on the Sudbury Neutrino Observatory helped shed light on the solar neutrino problem, which helped firmly establish that neutrinos have mass. His subsequent work, which continues to this day, builds on this discovery and hopes to shed further light on the nature and scale of the mass of the neutrino. He is a member of the Catron and Project 8 experiments, which use the process of tritium beta decay, originally proposed by Enrico Fermi, to measure the mass of the neutrino directly. Formaggio's group at MIT develops novel detector technologies and techniques to better understand the properties of neutrinos and other rare and exotic particles. In particular, developing the technique of cyclotron radiation emission spectroscopy to accurately measure the energy of electrons emitted in beta decay, now used by the Project 8 experiment. The Formaggio group is also developing new cryogenic bolometers to better understand neutrino interactions at extremely low energies. Such detectors are part of the upcoming Ricochet experiment, which aims to study the process of coherent neutrino scattering using neutrinos created in nuclear reactors. More recently, the group has been exploring the potential role of quantum sensors and quantum readout systems for the purpose of detecting neutrinos and other weakly interacting particles. I also want to mention that Professor Formaggio is an inaugural member of the SURF Science Program Advisory Committee, providing sage advice regarding facilities, support, and experiments appropriate to SURF. I've known Dr. Formaggio for many years now, starting from our time working together on the SNOW experiment. Now let's get ready to explore the very intriguing topic of neutrino lasers. Dr. Formaggio.
Hello, everyone, and thank you, Jared, for the very kind introduction. I'm very excited to be here, so thank you again for inviting me. As Jared mentioned, I do a number of different projects related to neutrino mass and detecting neutrinos, and I'll be talking about none of that. Rather, I am going to subject you to a novel idea that we are exploring that was an outgrowth from my sabbatical about a year and a half ago, and that is exploring the possibility of a neutrino laser from Bose-Einstein condensates. So to get started, I need to make a little bit of an analogy from what more commonly we know as more familiar particles, such as the photon and the neutrino, because there are some very common properties between them, and then some very distinctive properties that are different. So for one, you can think about the mass of either the photon and the neutrino. The photon mass is zero. That's guided by theory, and it needs to be exactly zero. The neutrino was almost considered a massless particle until, as Jared mentioned, the Sudbury Neutrino Observatory and the Super-Kamiokande experiment showed that this is not true, that in fact neutrinos do have mass. You can think about how they interact. So the photon interacts electromagnetically, whereas the neutrino can only interact weakly. Different interaction mechanisms. Um, and also related to the mass, you can always think of the photon as going at the speed of light. The neutrino, because it does have a mass, means that it's not quite going at the speed of light at any given time. Um, the other major difference, however, between the photon and neutrino is that on the former, the photon is considered a boson, and so obeys boson statistics, whereas the neutrino is a fermion. And as we will see, this plays a very important role in what I'm about to say. But in either case, both of them have to obey the rules of quantum mechanics when they interact with other particles. So we're going to explore some different examples of quantum coherence, some analogies that we have, and the more familiar territory is done with photons, but neutrinos also participate in this. And three clear examples where we can see quantum phenomena in full display. One is neutrino oscillations, which led to the discovery of neutrinos having mass. Coherent scattering is another example where a coherent process that's guided by quantum mechanics is in display. And finally, the one I'm going to talk about, that's the crux of what I'm going to present, is on super-radiance. And this is what Chat GTP thinks all these different mechanisms look like um, if you query them. So I'm going to start with neutrino oscillations. There are numerous analogies that exist between the phenomena of neutrino oscillations and optical phenomena where you're involving a photon. Um, One example is you can think about the interference of the neutrino mass states with different wavelengths because each neutrino species has a slightly different mass, and so they have a slightly different wavelength. And as they propagate from one place to another, um, they combine differently. And one analogy of this is thinking about photons that's going through, a prism, and how the light recombines in the prism affects sort of what polarization you see on one side to another. And so the phenomena of oscillations is very akin to mixing of different states. In this case, the states are the different neutrino species, which have these slightly different wavelengths. In fact, one can mimic neutrino oscillations by even with photons directly. And so there's this very nice paper and really a homegrown experiment where you can set up a light source that goes through a bifringent crystal. And as the neutrino passes through, as the photon passes through, it mimics exactly what you would see for neutrino oscillations, where you have this mixing between different states. So this is a nice little lab setup by a colleague of mine, Christian Wernheimer, about a decade ago. And so you can do neutrino oscillations in the lab, obviously without using neutrinos. Um, if you write down sort of the formalism for what neutrino oscillations look like, this again looks a lot like neutrino optics. And in fact, you can express all of these expressions in terms of Pauli spin operators in order to understand neutrino oscillations in a simple system. To one of the fun projects I did many, many years ago was sort of explore whether some of the predictions that are available in optical phenomena, for example, testing Bell's theorem, could be done also with neutrino oscillations. And it turns out that one can do that. And there is, because of this correspondence between neutrinos and photons, you can make an argument for testing Bell's theorem. So this was work that was done quite a bit ago, and that's basically looking at correlations between different species. And the trick there when we tackled this problem was trying to cast everything that we know about neutrino. I'm a neutrino physicist, so I I constantly think about how to express things in terms of neutrino physics, but I had to recast things in terms of observables that were more common in optical experiments. And what that sort of led to us was trying to formulate oscillations as a correlation between different neutrino species. That exercise was quite a bit of fun, and it led to a very nice uh, paper that allowed us to test not exactly Bell's inequality, but an analogy of it, known as the Leggett-Gard inequality. So you can think of Bell's inequality as being a space-like test of quantum mechanics. Leggett-Gard, you can think of it as a time-like test of quantum mechanics. And it turns out that oscillations can be mapped directly into this observable. And then we went ahead and looked at data from oscillation experiments. In our particular case, um, we looked at the Minos data because it was the most relevant that we could have access to. And we're able to show that the observable of the violation of Leggett-Gard's inequality could be seen in neutrino physics. Now, this wasn't completely loophole free, but it was one of the longest tests at the time of a Bell-like inequality over a very large distance. Okay, so that was one example where you look at oscillations and you recast neutrino oscillation physics in terms of things that are sort of more fundamental quantum tests. There's another example in neutrino physics where this is done, and that's in coherent neutrino scattering. So I'll bring up that second analogy. And here, the case is that typically for neutrino physicists, we're dealing with neutrinos with very high energies. And when a neutrino comes in and interacts with a nucleus, usually the wavelength is really small because it has a lot of energy and therefore it's very high momentum. That neutrino then probes an individual neutron or proton inside of the nucleus. Um, and uh, the higher the momentum, the finer the probe in seen inside the nucleus. Now, you can relax this condition. So you can imagine the case where if you instead have a neutrino that has very small momentum, typically, this is easier at lower energies because the neutrino mass and momentum are linearly proportional to each other. But if you have a very low energy neutrino, which is equivalent to a low momentum neutrino, now the bright wavelength that you use to probe is getting much, much bigger. And at this point, picking out an individual proton or an individual neutron becomes much more difficult because you can't distinguish within that wavelength which neutron or proton you have excited. And in quantum mechanics, whenever you have this, you have to remember you always add the amplitudes and then you square them to get the probability of interaction. And in this case, these amplitudes for the different neutrons and protons are all coherent because you can't distinguish them. And as a result, you get this amplification in the cross section. This was an idea that was brought forward and published in 1974. It was actually very close to my birthday by one of our MIT colleagues. And here, the cross section has a number of components, so you can calculate what the cross section for these neutrinos at very low momenta undergoing this coherent scattering. It's proportional to the neutrino energy squared that comes out usually when you look at neutrino scattering. But the coherence effect is amplified by this n squared term, which is essentially the number of effective neutrons and protons inside of your nucleus. So this was proposed now near over 40 years ago. I guess now 50. I'm much older now than 40. And it took a long time to be experimentally verified, and that's because the signature for this is a very tiny momentum recoil in your nucleus. However, it has been finally experimentally observed by the coherent collaboration in 2017, I believe. So there's another example where you have a coherence effect happening within the nucleus. And now I'll talk about another potential aspect of this, which is the idea of super-radiance. So you can think about, well, one is a neutrino not like a photon, and then that comes out whenever the neutrino, when something is dependent on the fermion boson properties of the particles involved. So one clear example of this is lasers. So lasing, it relies on the coherent amplification by stimulated emission. And in laser amplification, neutrinos would not be permitted to do this because you can't occupy more than one fermion in a given mode. You're either limited for it to be one or for it to be zero. In math terms, you can think about the commutation between operators. And for bosons, they obey the commutation relationship where the commutator is equal exactly one. In that case, then you can have this term be much, much greater than one. But for fermions, this is not the case, and they obey anti-commutation rules. And as a result, this 1 plus n factor does not realize itself. And usually when people think about a laser, they're honing in on this amplification because they're bosons. Now, so that method in itself won't work. And we consider a different optics enhancement for this, and that is the idea of super-radiance. So this was an idea proposed by Decay in 1954. Here, this is a super-radiance is a collective spontaneous emission from many atoms that individually are doing their own thing, but coherently contribute to enhance the radiative decay rate. And of course, this is with photons, but this is the analogy we started to look at. Now, for superradiance to occur, usually one of the major conditions for this is that the photon wavelength that's at play must be much, much larger than the atomic spacing. So effectively, it's similar to the idea that we talked about with coherent neutrino scattering. You have this very large wavelength, and now each of these atoms is indistinguishable. And if when they are when they're indistinguishable, then each one amplitude doesn't know the other, and you get this collective effect. But if the wavelength is too small, then you can start to pick out individual atoms, and then the effect disappears. And in fact, people have experimentally shown superradiance, of course, many times over. And usually the signature is the scaling that goes that the burst goes from an exponential type of decay to a super radiant burst, where you get the bulk of all your decays happening when you have about half the atoms have decayed away. So you get this burst of neutrinos rather than this steady decay rate that you expect from exponential decay. And this, of course, has been seen many, many times over. One can ask whether you can make super radiant lasers. In fact, people have done this, even with very high energies. So this example on the right is from a group that have done this for ultraviolet xenon. And there are other examples of this. Um, Usually here, the photon has a chance to escape before it can interact with other atoms. And what that implies, if the photon escapes before it interacts with other atoms, is that effectively the photon occupation number inside of that sample is below 1. So unlike our laser case, we do not necessarily rely on the fact that the occupancy of the exiting particle be greater than 1. We have examples where this occupancy number can be less than 1. Okay, so we can consider, we have seen some different experimental examples of superradiance with photon systems. We can look at this a little bit more closely at sort of what's involved. We usually work in the simple two-level system where we have n atoms. And typically you can cast them in terms of you have some excited state and you have some ground state, and you transition between the two by ejecting a photon. Um, Formally, you can construct ladder operators to move from one state to another. So you can either excite the case, your atom into the excited state, or you can de-excite the atom back into the ground state. These two operators don't commute, and so you have a commutation relation between them that's non-trivial. And when we talk about a collection of atoms where you have two level atoms that are all interacting with some external source, and they start to be indistinguishable, then you don't no longer have the luxury of distinguishing one atom versus another. And so you consider the whole sum of those operators together. And this allows you to write things in terms of energy eigenstates. And there you change your quantum number. So instead of thinking about this many excited states and this many ground states, you just have some collective total spin state, J, and where you are in the system. And so you span across between being all in an excited state and then moving down until you're all in the ground state. And if you write down the Hamiltonian for this, usually you can distinguish different particles because each individual atom has its own momentum and its own radius. And so typically these are distinguishable. But if your photon wavelength is very small compared to the size of your system, then we satisfy the Dickey condition in that all those different phases are effectively one. And that allows us to just write down one large operator without worrying about each individual one. So this is the idea that the different excited and ground states are indistinguishable. So in this case, the condition just has to be that the momentum and the size of the nucleus are much, much less than 1. And if you recall a few slides back, that was one of the conditions we had to have in order to see superradiance. Okay, so then you go through and you calculate what the rate of decay should be, and you find that in a simple system, and of course, there are many ways to write this, so this is just one manifestation of it, that you get this enhancement of 1 plus how many atoms or excited states you have in the system. And if you then calculate your decay rate, you get this enhancement that goes like n squared, which is what is usually seen in the experiments I talked about. You say, okay, great. Why don't we just go ahead and do that for neutrinos? And immediately we start running into some problems. Well, before I talk about that, I just want to mention that super-radiance and stimulated emission are not necessarily um, the exact same thing. And as I mentioned before, there are experiments that have seen super-radiance, even though they have this occupancy number to be much less than 1. And the idea here is that the coherence that we're kind of seeking after is stored within the gain medium of your system. So you can think about the correlations between the different atoms as being key for this super radiant effect to take place. Okay, so now we want to see whether weak decays also obey this idea of super radiance. But we, in this case, the uh, particles that are emitted are fermions rather than bosons. So we're no longer getting rid of just one photon. What we have is a fermion-antifermion pair that escapes. So the process that we looked at was explicitly electron capture. So we have different ways of decaying using the weak force. So we can have beta decay. We can, but where you you have a three-body system escaping. But the case that we studied was electron capture. And in this case, you capture an electron within the nucleus. This happens at some rate for radioactive isotopes, and out comes a progeny, which is a fermion, and a neutrino, which is also a fermion. So because of the way that the weak force is formulated, because it's changing isospin states, we can use a lot of the same tools that we used for our photon case and apply it to these weak decays. At low momentum scales, this actually works very well. And in this case, the operators that I showed before are not necessarily spin operators, but they're isospin operators, where they're changing the isospin of your nucleus. But the formalism, or the way you write down your Hamiltonian, is very similar. So again, we have a raising and lowering operator that take us from one state to another. These operators don't commute, just as before, and so their commutation relationship is shown and looks identical to that of the spins, and those commutation relations still hold. But already we got one problem, and that's because if you write down the Hamiltonian, you have these neutrino operators in there. And when you write out what this looks like to first order, you get a term that looks like instead of 1 plus the state, but you have 1 minus the state. This is the Pauli exclusion principle at work and forces this process to either be 0 or 1. So already we run into a problem. Now, the condition for Pauli exclusion is that that fermion can't occupy the same space as another fermion. So we made the ansatz that the neutrino that is in the process goes ahead and leaves the system. And this is not unreasonable. One thing that neutrinos do really well is not interact with things and go almost at the speed of light. So the neutrinos would then exit the system, and that allows the system to have effectively the equivalent of the neutrino density being 0. And now our Hamiltonian looks slightly different but still has this raising-lowering operator at play. And now we run into problem number 2. So although there doesn't appear to be anything in principle that prohibits super-radiant emission from fermions, um, it does require that the wavelength of the atoms be much smaller than the size of the atoms. So recall back that one of the reasons that we could write that effective Hamiltonian is that we couldn't tell a particular atom apart from another one. And for photons, that's not a big deal. Photons usually involve energies at the eV scale, and so the wavelengths are really large, and so it's easy to capture a lot of atoms in that envelope. But for almost all beta decays and electron capture decays, we're talking kiloelectron volts to mega electron volt energy scales. So you can't exactly you very quickly become able to identify who is decaying in your process. And so that aspect of indistinguishability is not there. Okay. So how do we overcome this? I mean, this is a deal breaker in many respects. Well, we went back and tried to think, well, is there a way in which that information about which particle emitted did the emission is hidden or indistinguishable? And one way you can have this happen is if the atom itself is not defined. In other words, that the atom itself is indistinguishable from any other one. And the condition where this actually occurs is when you have a Bose-Einstein condensate, where you have different atoms, but because they're bosons and they're all in the same, occupy the same state, they are indistinguishable from one another, and they have very high correlations with one another because they are spatially connected. So in our original case, we had a bunch of emitters where the atoms' wavelengths were very well defined, and so whenever they emitted decay, we could go and look at the emitted neutrino or the emitted progeny, trace it back, and say, aha, this particular atom has decayed. But in a Bose-Einstein condensate, where they all occupy, some number of them occupy the same exact state, then when you look back, even though you can say exactly where the event happened, you cannot say which atom decayed. And that indistinguishability, again, allows us to do what we did before, which is not write the operators as a sum without this phase decoherence that destroys this effect. So when we do that, and we then compute our rate, we get something that looks a lot like what you expect for supercoherence, where you have the rate of decay that is now dependent on not just exponentially, but grows as n squared. And when you look at the rate of growth of neutrinos from a radioactive Bose-Einstein gas, you can see that if you have no superradiance, you get the dashed line on the right. But as you add more and more atoms in your population, then the decay happens faster and faster. And typically it scales like the typical decay rate divided by the number of atoms in the Bose-Einstein condensate. We went ahead and so this was work. I'm sorry I didn't say this at the very beginning, but really this was inspired by many conversations that I had with Ben Jones, and he really did drive a lot of the intellectual work here. So I'm greatly indebted to him for uh, uh, talking this idea with me over many Slack messages. Um, this led to a publication, which is now on PRL, and there is a link at the bottom of my slide in case you're interested. So the prediction here is so we wanted to look at Bose-Einstein condensates that have been done before. And we picked on rubidium as a test case to look at it. And it turns out that rubidium is actually an excellent case for one to study. So rubidium-87 is routinely and relatively easily cooled to Bose-Einstein condensation. It There's another isotope of rubidium, which is rubidium-85. This is a little bit more complicated to cool because it has some hyperfine structure. And just down below, there is an isotope called rubidium-83 that's, to our knowledge, has never been turned into a Bose-Einstein condensate, but it is a boson, and in fact can be cooled sympathetically because its cross section is very similar to that of 87. Its half-life is typically 82 days, so about 3 months. Um, and if you're able to cool down about 1 million atoms, this decay rate drops to about 3 minutes by the rule that I mentioned before. Um, and so this is quite nice because the rubidium, you have some time to sort of get things to work to make sure that it doesn't all decay away before it's too late. But if you're able to condensate it the same way as rubidium-87, you will see an effect fairly easily. Its signature is also quite convenient because it decays into uh, an excited state of krypton called metastable state of krypton called krypton 83. This happens to have a half-life of about 2 hours, and it produces a monoenergetic electron when it decays. We're familiar with this because this is our calibration source for our more standard experiments with Project 8 and Catrin. By the way, this is not the only uh, candidate Bose-Einstein condensate that has a electron capture isotope. You can also do this with dysprosium. You could do this with cesium, which I don't show here. The reason why we got interested in this at all was because we were exploring atomic tritium, because atomic tritium is an important aspect of our research for the Project 8 neutrino mass experiment. So we were thinking of, well, what else can we do with an atomic Bose-Einstein condensate made of atomic tritium? And that got us thinking about Bose-Einstein condensates in general, and this is where the idea sort of blossomed. Now, is this idea robust? Um, so, uh, one question you can ask is super-radiance really allowed for fermions? By our accounts, we don't think there's anything that specifically prohibits fermions from exhibiting super-radiance. But this is a reasonable place of scrutiny. And as I mentioned, I will mention in the next few slides, this is a very active place for critique. Um, you can also ask whether the high energies of the neutrino or the decay product, which translates into very high momentum, spoil this coherence. And we point to the fact that this indistinguishability factor plays a key role here, because even though you're able to pinpoint where the event happens, you're still do not know which atom decayed because of the coherence that exists between all the different atoms inside your BEC. Um, and another question is, well, what if I go and take a detector and I start interfering with the emitted krypton or neutrino? And in other words, I interfere with it. And we also think that this does not affect the process. And that's because in our particular case, you can decohere typically if you're coupling to some environment nearby. And usually this means that you're able to distinguish one particle versus another. But in our case, our two particles still remain indistinguishable. So I still can't tell which particle decayed. And therefore, any decoherence that occurs there is common to all. And so it gives me no information about which atom decayed. And therefore, we still maintain that the system would decay much as it would if you didn't observe it. We have a small, more detailed version of this idea in our paper. We think that this is probably enough that we would love to see it tested in the lab. Um, so, for one thing, this would be something where coherence would appear even though the scale at which things are happening are much, much larger than the typical EV scale of photons. Even though the recoil can transfer information about its surroundings, because we still can't determine which parent decay atom has decayed, we think that coherence will be maintained. And the only real caveat for this to work is that every decay needs to be identical to the next one. So we have our condition for meeting these requirements is that the sample needs to be emitting this decaying in exactly the same way for each decay. And that means that it's guided by the lifetime of the BEC itself. And so as soon as the parent atoms start to decohere, then the decoherence is lost there. Um, we tried to see if this had been thought about elsewhere. We found some examples a little bit after our paper that explored this. There was a group, Avestian and others, that proposed looking at the collective decay of positronium in the Bose-Einstein condensate. So that is not involving the weak force, but in a very similar case where you have two very energetic photons escaping the system. There was another group that proposed looking at this with cesium-135, where you have a high energy photon escaping. So those two proposals, again, only involving photons, not neutrinos, but in a similar mechanism. Um, then we also looked at the literature to see if there are any papers that looked at exploring Dicke states for enhancing neutrinos. And actually, there was one. This was by Varnati and apologies, I can't pronounce their names correctly, but Dimopoulos. They proposed looking at super-radiant interactions here where um, the atoms are or the target. So looking at neutrino scattering rather than enhanced decay. Um, and so this is not necessarily requiring a Bose-Einstein condensate, but a lot of the same ideas of using Dickey states have been explored in that particular paper, which I apologize that my slide did not capture um, the journal, but I'm happy to tell people if they're interested. Okay, so that was what I showed before was sort of the status of things a few months ago. We can ask, well, what has been the reaction to this idea? Some of it has been positive. I was happy to see that MIT News turned it into a story, and the best part about that was the graphics that they generated. So I'm fond of that. And we were highlighted as one of the physics magazine's papers of 2025. So that was kind of nice, and I'll pat myself on the back for that. Of course, as I expected, there's also been great people have been skeptical, as they should have been. So there is two papers looking at this idea very critically. One by Blasone, Gastaldo, and Romeo that explore this idea and look at the limits due to Fermi statistics, and two papers from the Caroly group looking at the impossibility of a super-radiant neutrino laser. The critiques, the Caroly and all group, and of course I won't capture all of the arguments here, but the idea of both the non-locality of the decay atom and in their separate paper, looking at the coherent fermionic nature of the decay precludes any coherent advanced decay from the process. The Blasone paper argues that the fermionic nature of the neutrino and the progeny prohibits enhancement. However, they have this interesting side note in their paper, which say that if you make coupled paired fermions in their system, in their mind, they're thinking a molecule that undergoes electron capture, where each individual atom undergoes electron capture, then this leads to a what they refer to as a dynamical explosion that is far more, even more pronounced than what we predicted. So they refute our idea and then put in their own idea, which is even more explosive. So I thought that was very interesting, and I'm still kind of learning about their two papers. So you say, okay, well, maybe this is just not to be. But we started to really explore sort of the assumptions behind this. And it is our contention that in both cases, there is an explicit assumption that the coherence due to any of and all of the atoms they're basically have to be locally confined to the Bose-Einstein condensate. Um, in other words, the moment, say, for example, your neutrino and your daughter nucleus come out of the BEC, then they're lost to the world, and you can't enhance things that are not in your system locally. And even if you made them slow enough so that your daughter particle is still there, and could accumulate, then Pauli's principle kicks in and says, no, you can't do that. And so the effect is effectively forbidden. And I refer to the previous two papers for the details on that. However, we conjecture that in both cases, we are talking about highly entangled particles. Um, so every time the neutrino and the progeny escape, they are produced in the BEC. And because you can't tell which atom it is, that this entanglement is retained even if your outgoing particles are not local. Now, this was an idea that we sort of had in mind, but had none of the mathematical backup to say, yeah, well, they're entangled, so therefore they should preserve this. But luckily, Ben Jones again comes to the rescue, and he was able to locate this paper by C.K. Law that is exploring the idea of quantum entanglement in composite two fermionic systems. So in this paper, he basically asks, well, when you have two entangled photons, can they act like an effective boson? And it turns out that for highly correlated systems, um, that indeed this can be the case. In fact, when you have a highly correlated system, the effective operator that is there acts like a boson. Um, and the paper that I cite here is one example where it looks at this, but effectively it forces you to define um, your operator in terms of entangled states rather than individual neutrino or decay particle. And in the limit that these two particles are highly entangled, the commutation relationship between them is the same as that of a boson. And to the analogy that's sort of in mind is the BEC itself, because if you think about it, the BEC is composed of a bunch of fermions which have very different momenta and occupy the same space. So why do we have BC at all? And it turns out because you have a bunch of colorations, in this case, they're spatial colorations, between the different fermions that allows you to maintain and have the system act in a bosonic way. And it turns out that this requirement does not require the individual particles to be local. In fact, there's in one of the papers that cites Law's idea, which is cited at the bottom of the slide, they state, going through this argument of what the conditions for this coloration leading to these fermions to be non-local, it says, taking this idea to its logical conclusion, Law notes that two particles can be highly entangled even though they are far apart. Could we treat such a pair of fermions as a composite boson? The above analysis suggests that we can do so, and that the key here is that it's the pair's entanglement that leads to whether uh, you can treat these as bosons rather than fermions. We're still working on the details of this corollary, and I'm very grateful that Wolfgang Caroli is only a few floors down, and so I occasionally bug him with a question, and he replies with very deep answers that I have to think about. So we're still working through the details, but please stay tuned. But the whole point, I told Ben when I was working on this that this was either going to be my best paper or my worst paper. Um, but it's certainly been my most fun paper. So I hope you have once again wasted 1 hour listening to me on a crazy idea. Here we have introduced the idea of using a radioactive BEC to study enhanced neutrino emission through superradiance. And we have identified a scheme by which to test this idea in the laboratory. And if it's true, then we would have a benchtop type experiment where we can really study for the first time some very deep questions in quantum mechanics in a neutrino-based setup. And I'm very excited to see what experiments will yield on this. And with that, thank you again for listening, and I'm happy to answer any questions.
Wonderful. Thank you, Joe. Fabulous tour through some quantum mechanics associated with this really interesting idea. For those online, just a reminder, if you have a question, you can put it in the Q&A or raise your hand and we can unmute your mic so you can ask that question live. There is a question here I can put to Joe. In the case of fermions, the probability amplitudes may cancel because of antisymmetric wave functions. Will it reduce the intensity? And if so, then how does the intensity scale with the n squared?
So I believe it goes back to whether you can treat the entangled pair as a boson-like effective particle. So if and maybe Wolfgang, I see his hand raised, so maybe he may want to clarify the question. Hi, Wolfgang.
Go ahead and unmute, Wolfgang. I think I gave you permission.
Yeah, hi Joe. Nice overview over neutrino physics. I don't think the Bose-Einstein condensate solves the problem of short wavelengths. We have studied experimentally and quantitatively super-radiance of photons coming out of a Bose-Einstein condensate. And we know because the wavelengths of light is shorter than the size of the condensate, we are not getting an n times enhancement. We are only getting an enhancement by the optical density. So if I use that and scale now the wavelengths from micrometer to MeV, where the wavelength is picometer, this is a factor of 1,000,000, I lose in gain 1,000,000 cube. So just using the known super-radiance, which has been quantitatively studied in Bose-Einstein condensates, and assuming that what is emitted are now MeV neutrinos or MeV photons, we would lose 18 orders of magnitude, which shows for me that super-radiance in Bose-Einstein condensates at MeV energies is not possible.
Right. Hi, Wolfgang. For those in the audience, the details of that are in a paper that Wolfgang's group has put out. We still disagree, and the main thing that we're focusing on is the fact that although that's true for the individual neutrino and the individual progeny that comes out of the decay, that their wavelengths are indeed much smaller than BC would allow. The fact that the two are entangled with one another and with all the other atoms in the BC, it's really the pair of the neutrino and progeny particle that makes that defines that limit, and that manifests itself is whether when you have one decay and then you wait for the next one, whether the system and going from time TA to TB has changed at all. As long as the process of decay is identical to the next one, I think we circumvent that limitation compared to what happens when you have spatial relations. But I know we disagree on this point, and I'm hoping that either we prove ourselves wrong, or we prove we show otherwise.
All right. Any other questions? I know we're getting close to the top of the hour. Maybe I'll just ask one, Joe, in closing. You mentioned this phenomena being potentially a tool for exploring neutrino properties. I wonder if you could just, as we sort out what the phenomena can demonstrate, and any thoughts going forward into the future on the power of this phenomenon.
Yeah, there are a few. One, I think it's very interesting in that I think this is the only mechanism where you have two spatially separated but correlated fermions that still act coherently. So I think that's a great test, and I don't think there are many easy ways to do that. You can do it with molecules, but I think this is another test bed for that. And because the signature is such, then you would be able to um, uh, explore in a completely different platform. The other, of course, is, well, whatever the process of decay is reversible. So, of course, you may think, oh, well, maybe this is a venue for enhanced neutrino cross sections. If we have not explored that at all, we don't know if that's allowed. But one of the papers that I mentioned does explore this idea of a coherent system. And in that particular case, they were looking at the cosmic neutrino background as a source of low momentum photons, neutrinos that could interact with such a system. So I'm excited about that, but we have not really touched it in any great detail in our paper, and we're hoping smarter people will explore that idea.
Very good. Well, thank you. Let's go ahead and wrap up. Dr. Formaggio, a fascinating topic, lots of engagement. I can see why it might be your funnest topic to dive into. And thanks for sharing it with our audience. This talk is available to view and share on YouTube, Vimeo, and the institute.surf/deeper-talks webpage. Next month's Deeper Talk will be on February 11th at our standard time, 9 a.m. Mountain. The topic, updates on low background counting at SURF from the Black Hill State University underground campus, with featured speaker Dr. Brianna Mount. Your feedback helps improve this program, and we appreciate any suggestions for speakers and topics for future talks. Please fill out the short survey you will receive immediately following the talk on Zoom and in your email. And with that, thank you for attending again. Bye-bye.